we're going to talk about like the different factors that affect substitution and elimination reactions, right? That's going to be the core focus of this part of this section, right? So the key factors that affect the reactions and how to determine the mechanism. Right, because we're basically going to talk about two types of substitution mechanisms, SN2 and SN1, and then E2 and E1. SN2 is substitution, nucleophilic, and then it's bi, which is very important, bimolecular. And then SN1, same thing, but it's unimolecular. So I'm just going to put quotes here. So unimolecular substitution, bimolecular substitution. And that difference in whether it's uni or bimolecular is going to determine the rate law, is going to determine the factors that speed it up, the factors that slow it down. All of that is at play based on the reaction mechanism. So SN2 and SN1, and then E2 is elimination. And that's also bimolecular. Right. And then E1, same thing, but it's uni. Molecular, right? So we've already seen examples of substitution reactions, right? If you have, let's say, for instance, you have a substrate. Right, we haven't seen a lot of elimination reactions, but we have seen some. But now we're going to focus on the two different types, well, two of the different types of eliminations. But we've seen substitution reactions where you have some leaving group that's here, it's bonded, it's in a polarized bond with carbon. And then that reacts with some nucleophile that comes in and displaces, like so. Boom. Oh, well, sorry. Here and then here, right? So then you end up with the nucleophile, again, substituting for your leaving group. And your leaving group leaving as an anion in most cases, not all the time, but in most cases. Right, so that's one example of a substitution. We've seen that already. And then we've also seen elimination, but not in the sense of losing of a leaving group. Not, we've seen other types of elimination where we form pi bonds and things like that. But here we're going to mostly be focused on if we have something like this, where this is a leaving group, and then we treat it with a strong base. Right, what we're going to end up with is right, the loss of a leaving group, the conjugate acid of a base, and then an alkene in the product, right? All right, because every time you do an elimination, the major product is going to be a pi bond formed somewhere, whether it's a carbonyl pi bond or whether it's a carbon-carbon pi bond, doesn't matter, right? So we're just going to dive in with these substitutions. I have two examples on the handout that we're going to work through for substitution. And so there's some kind of rules of thumb when you're doing substitution, and especially if it's SN2, right? There are a lot of factors to consider, all right? The first thing is that your substrate or your electrophile, since we've already talked about nucleophiles and electrophiles, right? This is my electrophile. And again, if you're looking for where the electrophile is going to react, always look for that most polarized bond, right? And the carbon that's partially positive is going to be the place where the electrons are accepted from the nucleophile. So this is my substrate. This is my nucleophile. You can see sulfur has 3 lone pairs and a negative charge, so it's ready to react. All right, and so now I'm doing this, and so let's look at the substrate first. The substrate is secondary. Everybody agree that that's a secondary carbon?
Are you saying that there's carbon on the left and the right side of where bromine's attached?
Yes.
Okay.
And this carbon right here is the reactive site. So we're calling that carbon secondary. So this is a secondary carbon, right? And it has a good leaving group. All right, and we're going to talk about how to determine how good the leaving group is, all that stuff. Because the things that we're going to talk about, we've already talked about in some capacity. So it has a good leaving group, secondary carbon. We have a good nucleophile, and then the solvent. This is important. This solvent, acetone, is what we call aprotic. It's aprotic, right? That's very important. So let me add a page so we can talk about this reaction in more detail. I'm just going to cut it and put it down there. All right. So first, let's look at what we get as a product, and then we're going to talk about how to determine if the leaving group is good, what does aprotic mean, all that stuff, and why aprotic solvents are important for SN2 reactions. All right. So the way this is going to happen, obviously my nucleophile is going to attack here at carbon, and I'm going to lose bromine. Anybody disagree with that? We've already seen these arrow pushing type mechanisms. Am I right?
Yes.
So my product, I'm going to have this. Right, and then in the place of bromine, I'm going to have this plus that. Everybody agree?
Yes.
Yes.
All right. So my nucleophile is going to attack my substrate and force the leaving group out. right? Bromine is, again, that's my leaving group. And they just swap places. The nucleophile swaps places with the leaving group. So let's talk first about the leaving group. We're going to really just beat this reaction to death and look at every single aspect of it. So let's talk about the leaving group. So how do we determine what's good and what's bad, right? We're going to use a familiar idea, right? What we want to do is look at the pKa of the conjugate acid of the leaving group, right? So this is bromine as a leaving group, which is literally the conjugate base of HBr. So the conjugate acid has a pKa of -9. Is that good or bad?
That's good.
It's excellent, isn't it?
Yeah.
So what that means is that when you lose Br minus, this is very stable. If it's lost as a leaving group, let me get change my pen.
Where'd you get that handout from, Dr. Russell?
It's in third module, but it's also in the chat. I put it in the chat.
Oh, wait, this part is part of the handout, same handout? Okay.
Yeah, it's just you just have to scroll down because I think it's like 6 pages. Right, so if it's stable as a conjugate base, that means it's going to be a good leaving group. So that's what we use to determine whether or not something is a good leaving group. We look at the conjugate acid pKa. And there's a chart right here. So if you have a question about whether something is a good leaving group, so a good leaving group, my G is ugly, sorry. I didn't mean to say that out loud. A good leaving group has a conjugate acid with a low pKa. Right, and that's just the leaving group plus a hydrogen, right? That's what your conjugate acid would be. Right, so that's how we determine whether or not something is a good leaving group or a bad leaving group. The reason that's important is because when you compare reactions and you want to know which one is faster or slower, then you need to have an idea about, and you're comparing leaving groups, you need to have an idea about which leaving group is good or bad, and there's a way to do it, right? Just look at the conjugate acid. All right. Any questions about that part? Right, so a good leaving group is going to have a conjugate acid with a low pKa. So let's go back up to here. So bromine, we know that that's our leaving group, and we know that it has a conjugate acid pKa of -9, so it's a great leaving group. It's actually excellent. All right, so we have an excellent leaving group. The nucleophile, let's talk about that real quick. And there's I think I mentioned this before in a different lecture, but there's a periodic trend, right? So nucleophilicity increases from left to right. I'm sorry, not increases. That's my bad. It decreases. It decreases from left to right, and it decreases from top to bottom across the periodic table. So across a period and down a group, it decreases in both directions. Right, so that's how you determine whether or not you have a good nucleophile or a bad nucleophile. You can compare it. If you're comparing nucleophiles, look at the position on the periodic table, and that'll help you, right? And let me put a caveat here.
I have a question.
Mm-hmm. Go ahead.
Can you repeat like the reason why it decreases going across and going down?
Sure. So a rough idea about why it decreases going across is based on the electronegativity. So as the atoms become more electronegative, they become worse donors, right? Because a nucleophile needs to donate electrons. So the reason it decreases left to right, one reason that we can, a plausible reason that we could say is that is due to increase in electronegativity.
Wait, backing off of like Tia's question. So that's the same trend you said for electronegativity? Or is
Yeah, it is. It is
Okay.
left to right. And then the only difference is the electronegativity increases from bottom to top.
Okay, yeah, I
It
remember.
decreases from left to right. But when we think about the left to right part of the trend for nucleophilicity, right, you can roughly say that it's due to increasing or increased electronegativity. Now the top to bottom part, you can say it's kind of roughly due to decreased charge.
Okay, because I was gonna say that fluorine had like, or I remember fluorine being the most like an electronegative.
Yeah.
Okay.
Highly unreactive too, very unreactive.
Okay.
But the reason it decreases from top to bottom is, I'm going to say charge concentration. Right, so the charge becomes more diffuse the bigger the atom is. So if the charge is more spread out over a larger surface area, then that's going to make the nucleophile less reactive. Right, so and again, this is a very nuanced topic, but this is the trend that you see, and this is what you can use to compare nucleophiles. We have some problems that we're going to work where we actually compare nucleophiles, right? So our leaving group is based on the pK of the conjugate acid. The nucleophilicity follows a particular trend. And then the solvent is also important. We want to do for the SN2 reaction, which is shown up top. We want to do this in what we call an aprotic solvent, right? So no H+ to donate. All right, we want to do it in a solvent that has no protons to spare. So you don't want to do it in like an alcohol or an acid or water. You want to do it in what we call a aprotic solvent, right? And let me give, we have a list of solvents right here, right? So acetone will be considered aprotic. Ethyl acetate, acetonitrile, I gave you the structures over here too, DMF, DCM, THF, all of these are considered aprotic. They cannot donate H+.
I have a question.
Go ahead.
Why does it have to be a product? Like,
oh, we're going to talk about it.
Oh.
Right. I'm just giving you, just defining the term first, but we're going to talk about why also. Right. So let me show you why And I'm also going to show you something else about the reaction as well. So this is just a matter of committing these to memory, right? Protic versus aprotic, right? Notice for protic solvents, these are the exact opposite. They can donate. Right, so anything protic can donate H plus. So any type of alcohol, acids, water, non-carboxylic acids, all those are protic. They all can give up H plus. So they're acidic, again, and then they give up H plus to your nucleophile, and that's not good. So let's talk about that. So here, one of the other pieces about the SN2 is the rate law. We said the 2 meant that it was bimolecular. Is that right?
Yes.
What that means is that it's a second order reaction. Right? So the SN2 is second order. It's first order in substrate and first order in nucleophile. Right, so the rate law is going to look like this. So rate is equal to the rate constant K times the nucleophile concentration and the substrate concentration. Oh. Right, so both the substrate and the nucleophile are involved in determining the rate. That's important because with the SN1, the nucleophile is not involved, so it changes. And the conditions change that facilitate it also. Right, so when we talk about the solvent being aprotic, in a protic solvent, no, let me not say that because somebody's going to read that and think it's aprotic. So if you do it in a protic solvent, what was going to happen is your nucleophile is going to get what we call solvated. Very important term, right? Let me show you what that means in layman's terms. It's like basically you put a fence around your nucleophile, but the fence is going to come from the protons that are on your protic solvent, right? So if I have my nucleophile here, let me use the one that's up top. If I use SCH3, which is negative, right? If this is in a protic solvent, protic meaning H plus donating solvent, all of those protons are going to come here and surround or put a fence around your nucleophile. This is again an example of what we call solvation, right? So if you do it in a protic solvent, it's going to solvate your nucleophile. Why does that matter? Because if we look at the rate law, you can see that the nucleophile is a part of the rate law, right? So let me make that plain. So if it's solvated, a solvated nucleophile, for lack of a better term, is lazy. They get relaxed, so they don't react as fast. All right, will not react as fast. So let me show you that in terms of an energy diagram. So again, this is time on the x-axis, and this is energy on the y-axis. All right. So let's say, for instance, if I do this in a Protic solvent, let me pick a different color. I'm sorry, I'm gonna start out with aprotic. Let's just say that's my reaction profile for aprotic. So this is my substrate. And then this is, let me do that in black. I don't like that. Right, this is my substrate. And this is my nucleophile. And then this is my products. And of course you have here transition state. All right. If I do this in and this is aprotic. Right. If I do this in a Protic solvent, what's going to happen is pretty drastic. So first of all, the energy of my nucleophile is going to drop. Right. So my nucleophile energy drops, but I'm going through the same transition state and getting to the same product. What changes? Can you see what's going to change? If this is the activation energy,
Will the activation energy be more?
higher, yes. Can you see it? So that gap right there is going to increase the activation energy. So the activation energy in the Protic solvent is going to go up because the nucleophile is lower in energy. Right, so this is the activation energy for the reaction done in a Protic solvent. So let me make that plain too. So this is Protic. Right, so that's why you want to use an aprotic solvent, because the Protic solvent is going to solvate your nucleophile, drop its energy, and increase the activation energy at the same time. All right, so a lower nucleophile energy because of that Protic solvent is going to increase activation energy, and that controls the rate, right? The activation energy controls the rate of the reaction, so it's going to slow the reaction down, so that's bad. So that's why you want to use aprotic solvents for SN2 type reactions. All right, does that make sense? Anybody not following or not catching it? So we know what the rate law is, right? Both the nucleophile and the substrate are involved in the rate determining step. So any changes you make to the nucleophile will affect the rate. Any changes you make to the substrate are going to affect the rate. I see two hands up. I don't know who was first though, so y'all gotta go ahead.
For the rate law, when you were writing that one is first for the second order in substitution, first
Mhm.
order in substrate, and first order in nucleophile, what does that
Yeah.
exactly mean?
So with the rate law, if you remember this or recall this from from Chem, when you write a rate law, there's an exponent here.
Yes, yeah, okay,
So first order means that exponent is 1.
got it,
And,
okay,
and it's second order overall because when you multiply the concentrations, you add the exponents.
okay, that makes sense.
Mhm. Who, I saw another hand up too.
I think it was an accident.
Okay, all right, cool. Any questions about the SN2? So what we know about it is good nucleophiles facilitated, good leaving groups facilitated. We know that we need an aprotic solvent for it to, be at optimal performance. And then one other thing that we need to talk about is the fact that it's concerted. and let me not say concerted, because it can be, a lot of times you'll have a mechanism that has multiple steps, but I'm going to say that it has a concerted rate determining step. Right, what that means is that it's simultaneous. Everything is all happening at the same time. Right, there are two types of reactions that can happen. You can have a concerted reaction, and then we're going to see for SN1, you can have a stepwise reaction. But the SN2 is concerted. All right. What that means in terms of how it happens is as your nucleophile is attacking your substrate, and I'm just going to use a generic substrate. Let's just use this. All right, so here's my substrate. And then I'm going to put like a bromine here. All right, here's my leaving group. Here's my nucleophile. Let me just use the same one. All right, all of this is happening at the same time. So the nucleophile is attacking. Oh no, let me say this. Let me say it a different way. So nucleophilic attack is simultaneous. Right, it's simultaneous with leaving group departure. So as the nucleophile is coming in, that's why I'm saying it's concerted, because as the nucleophile comes in, the leaving group is leaving, right? And so this is what the transition state would look like, or a transition state would look like for SN2 type reaction. You have your nucleophile coming in, your leaving group leaving, and the whole thing is overall has a negative charge. So that's partially negative. That's partially negative. This bond right here is partially formed. And then over here, this bond is partially broken. Right, in the transition state. So all of this is a consequence of it being concerted. Right, the transition state means that, and the fact that the nucleophile is involved in the rate determining step, that means that this is what the transition state has to look like, where your nucleophile is coming in and your leaving group is leaving, and it's concerted. So that means it's all happening at the same time. Right, so that's again, there are a lot of different aspects to these substitutions. You know, when we were looking at it before, it was just from an arrow pushing perspective, like how does the nucleophile attack the electrophile? But now we can see a little bit more mechanistic information for these reactions, right? What's one thing to put the arrows in, is another thing to understand, you know, beyond that, like what's happening with the rate, how can I increase the rate, how can I decrease the rate, so on and so forth. All right, so we're gonna look at another example. And for the second example, we're just gonna put the arrows in and put the rate law in and all that stuff. Right, so let's look at the second example here. This is my substrate. This is my leaving group. And this is my nucleophile. All right. DCM is an aprotic solvent. Right, it's on the list. So don't panic if you see a solvent and don't know what type it is. And the reason that this is all important is because, again, we can figure out what mechanism is at work, sometimes just based on what solvent the reaction is done in. You know, if it's done in a protic solvent, then you can almost bet that it's going to be one of your unimolecular processes, either E1 or SN1. If it's done in a protic solvent or aprotic solvent, then you can almost bet that it's going to be one of your bimolecular processes, right? So E2 or SN2. And that's a big clue. Like if you don't have any other information, you can look at the solvent and kind of tell from there whether it's going to be bimolecular or unimolecular. And then you can look at the products and tell whether it's a substitution or an elimination. But we'll talk more about that as we move forward. So what's the product here? What are we doing? This is an iodine is my leaving group, it's a great leaving group, by the way. It's right. And the carbon is, what type of carbon is that? Is it primary? Is it secondary? Is it tertiary?
Secondary.
Where's the other carbon bonded to it?
Oh yeah, it's primary.
Primary. So it's a primary. One thing about the SN2, another way to pick it out quickly is to look at the substrate. If it's primary or secondary, primary is only SN2. Secondary can be either or. Tertiary is only SN1, right? So primary and secondary substrates do SN2, right? But you can see right there, it's a primary substrate, good leaving group, really good nucleophile, and an aprotic solvent, right? So what does the product look like? And we can put the arrows in as well. So we can do this, boom, to here. Lose our leaving group, we put some electrons on it. If we just add in this,
Yes.
all right, and what would the rate law be for that reaction? How would we write it? If it's SN2, it's the nucleophile, concentration of the nucleophile times the concentration of the substrate. And then plus, we have to also include the rate constant K. Right? So that's the rate law, and it's also concerted. And we know that because it's a SN2, right? SN2 mechanisms are concerted. They all happen, the rate determinant step, everything happens in one step and not multiple steps.
I have a question.
Go ahead.
How can you tell whether it's SN2 or SN1 by looking at the reaction?
The reaction itself,
Yes.
one way is to look at the solvent. Again, SN1 is going to be favored in protic solvents. SN2 is favored in aprotic solvents. One way is to look at the substrate. If it's primary, then it's going to only go SN2. If it's secondary or tertiary, secondary, it's a toss-up. It can be either SN2 or SN1. So then you have to look at another factor, like the solvent or the product outcome. And then tertiary is only going to be SN1. So you really have to, that's why we walk this first example down, looking at the substrate, the solvent, the nucleophile, the leaving group, because all of those factors are going to help you to determine whether a mechanism is SN2 or SN1. But the two biggest things are the substrate and the solvent. If the solvent is aprotic, more than likely it's gonna be a SN2. If it's Protic, more than likely it's gonna be SN1.
I
Okay.
have a question as well.
Go ahead.
For the rate law, I remember in like Gen Chem like 1 or 2 that we actually like substituted, I guess, the concentrations. Or
Mhm.
we just leave it like the generic rate constant.
Yeah, for now, yeah, we'll leave it.
Okay.
Because we're not really concerned with actually calculating the rate.
Mm,
It's just a matter of showing you that it's bimolecular and it's second order.
okay. And then when you say bimolecular, you just mean that it's two, right? Like as in,
Two species involved in the rate determinant step.
got it. Okay. Thank you.
Yeah. Good question. All right, so if you get a chance, I sent an announcement out on Friday with a couple of videos in it. One of them is called the ICE method. And that's what we're going to be using to kind of distinguish between the mechanisms. So it's identify, characterize, and then execute. So make sure you watch that before you come back on Wednesday, because we're going to hit SN1, pull it apart the same way, pull the guts out and all the nuts and bolts. But really what you're going to find out is that the more we look at this, there's some similarities that you can kind of pick up on right away between the bimolecular mechanisms like E2 and SN2. And there's some similarities between the E1 and the SN1, right? So we're going to play those similarities up so that there's less stuff for you to try to memorize. If you just learn some of the basics for one type of mechanism, it's going to apply to the other mechanism, right? So that way you're not trying to memorize, oh, I got to memorize all this for E2. No, if you remember the concepts and the principles that guided the SN2, then some of those same concepts are going to show up again in E2, as far as the rate law, as far as the solvation and all that stuff is going to show up again. So Wednesday, we're going to hit the SN1. Hopefully we'll be able to get to E2 also. And then we'll do E1, and then we got a bunch of examples we're going to work through. And they're going to bring out different ideas about these different reactions. And there's a page in the handout right here, and it kind of goes through a lot of stuff I just talked about. But I like to talk about it instead of just throwing you to the wolves and just say, here, go read this, right? Because you still need a little bit of explanation. But with that being said, I'm gonna stop recording, and if I can find the box, and then I'll